Okay, well, good morning or good afternoon, everyone. It's Mr. Kinney. We're going over the nuclear and balanced chemical reactions page. So it starts off, you've got this periodic, this grid here, and what this is all about is just to reinforce for you that whatever period you're in, that tells you how many shells. Whatever group number you're in, that tells you how many valence electrons you have. That's the electrons in the outer shell. Now, when I made up this data table, I did make a slight goof. That pattern works for all the elements in what they call in groups 1 and 2 and groups 13 through 18. It doesn't work for the transition metals or the rare earth metals down here. So we just need to put a little X down there because those won't work. They don't follow the pattern on that. So when you go through these, I'm just going to do a couple here. But when you look on your periodic table, okay, you've got hydrogen, and it is in period number 1. Oh, I don't need to look at the periodic table. It's got one shell because it is in period 1. It is in group number 1 of the periodic table, which means it has one electron in its outer valence shell. I'm going to jump over here to our friend chlorine. Chlorine is one of the halogens. On this little chart here, it's not darkened in, but the halogens are unique of the nonmetals because they need only one more electron to be stable. It makes them the most reactive nonmetals. Anyway, chlorine is in period, let's see, it's 3 rows down, so it's in period 3. And that means it has 3 shells. If we were to draw out, make a Bohr model of it, we'd have to have 3 shells. It is in group 17, or the old group 7A. So we just take the last number of that, so 17 becomes 7 valence electrons. All the atoms, okay, it's group 17, and it has 7 valence electrons. All the atoms want to have 8 electrons, except for hydrogen and helium. They're so small, they only need 2. So all the other elements on the periodic table are going to try, in the next unit, to get an 8th electron up there. And then I'll just do one more over there. Our friend polonium over here that Marie Curie discovered. So that's, let's see, 1, 2, 3, 4, 5, 6 rows down. So that's in period 6, which means it has 6 shells. It's a pretty big element. It's down low. And it is in group 16, the old group 6A. So it's in group 16, which means it has 6 valence electrons. So you can just follow that pattern for the rest of them. Number 2, draw and list the charge and mass and locations of the 3 subatomic particles. So I want you to draw a diagram of an atom. You'll see them on there. We've got the nucleus here with protons with a plus charge, and we've got neutrons with a neutral charge. I'll just draw it like that. You've got shells, the electron cloud, energy levels, whatever you want to call it, with electrons spinning around out here with a negative charge. Let's see, this is the shell. At least that's what they used to call it. Then now we call it energy levels. As you get to higher models of the atom, energy levels, etc., or orbitals and such. And then we've got the nucleus here. Nucleus is positive charge because it has protons and the neutral neutrons. And then the shell has a negative charge because it's full of electrons. So I think I've drawn that for you out. Number 3, explain how the number of each subatomic particle is determined for boron. Well, you look on the periodic table, and for boron, you've got this. So I'm just going to draw a quick square there. Boron has atomic number of 5, and it's 10.81. So protons, you look right there. It's just the atomic number. Oops, let me go over there. So that's the atomic number. Tells you how many protons. And it's also going to tell you how many electrons. Is also the atomic number. Easiest thing to tell. Any element on the periodic table, you instantly know how many electrons and protons it has. Then for neutrons, you've got to subtract. So neutrons is going to be the mass minus the atomic number. So on this one, since we got 10.18, we've got to round that to 11. So I'm just going to put 11. And then the atomic number is 5. So when you subtract that, you're going to get 6. It's important that you make sure you round that to the nearest whole number, then you subtract the number of protons over the atomic number. Number 4, how is the mass number different from the average atomic weight? Well, the average atomic weight is what we see on the periodic table. It's listed on the periodic table. Answer that and get a message. So that's right there. And it is an average of a whole bunch of atoms. The mass number, which we normally see if we've got an element like, carbon 14, or if we write it in isotope form like this number up here is telling us that's specifically what the weight of that element is, how many neutrons and protons are in its nucleus. Where on the periodic table, you're getting an average weight, and if we're using that to figure out number of neutrons, you got to remember to round this up to the nearest whole number. Number 5, what are isotopes? Okay, they're heavy or light elements. Heavy or light elements. Which means they have more neutrons or less neutrons than the most common isotope. So we've been studying carbon a lot. The most common isotope of carbon is carbon-12, the one that has 6 neutrons in it. But there's also carbon-14, a slightly heavier version that has 2 more neutrons, and we can use those in radioactive dating. So the way that isotopes differ is number of neutrons. It's the neutron number. Let's see on there. So why does an atom's mass number not always equal the atomic mass? Well, the mass number is real specific. If we use the analogy in class that if we take the average weight of everyone in this class, we'll have an average weight, but each of you have your own specific weight, and that would be like the mass number. Specific, SPECIF, specific, where the atomic mass is a general number. It's an average. Right there. So they're very similar. They're both telling you how many protons and neutrons, but the mass number is super specific. And uranium-235, for example, would tell you it's the isotope that has that mass number. Let's see, number 6. What are the horizontal rows? The rows are periods, and the vertical columns are groups. Like the word. Okay, so that's pretty straightforward. And groups are directly related to valence number of electrons. Valence electrons. Periods are the same as how many shells. Shell number. Pretty cool. Okay, for number 7, I'm not going to take time right here to do this. You've got a colored chart. You can look in your textbook. We colored in a diagram like this to go through all the different family members. I mean, you've got the transition metals, the rare earth metals. You've got the alkali metals, the alkali earth metals. Along the zigzag line are the, what do they call them? The metalloids or the semi-metals. We've got this special group here that we highlighted on your charts, the halogens. We have the noble gases. So you can look that up, and there will be questions on that. You'll need to know which ones they are. And I think that's question 7 and 8. So that's just a matter of looking that up yourself. Number 9, atomic radius. So this is part of our periodic trends. Well, atomic radius really is going to be, what's the radius from the nucleus to the outer part of the shell? So it's just a measure of the size in nanometers. You don't have to have that part, but it's just the size of the atom, size in nanometers of atoms. Electronegativity, that is the ability of atoms to attract electrons. Ability of atoms to attract electrons. And the trend is on the periodic table, I'm going to come over to this one. This side of the table, electronegativity is really low. Metals don't need electrons. They've got extra electrons. They're actually going to try to throw them away. These guys right over here, the halogens, they really need electrons, and they have the highest electronegativities, and they will pull them with, they will hold on to their atoms and they will electrons, and they will fight other elements to get their electrons. They will steal them. So, number 10, what are the trends for electronegativity as you go across the periodic table? Well, it's biggest with fluorine. I'm going to draw a big circle, fluorine, and then down here, cesium or francium is really small. So they're really large here. The sizes get smaller as you go across. As you go down the chart, the electronegativities get smaller. The closer an atom is to fluorine, the greater its electronegativity. So, for example, I'll ask period 2 right now. What's going to have a higher electronegativity, oxygen or nitrogen? Oxygen is closest to fluorine. It'll have the higher electronegativity. How about oxygen or sulfur? Which one will have the highest electronegativity? You're like, well, they're both right next to it, but as you go down, it gets smaller. So sulfur would have a smaller electronegativity. Sulfur doesn't need electrons as badly as oxygen does. So that's how you could work that out. Which element has the largest value? We answered that, fluorine. Why do electronegativity values change the way they do? As you add protons to the nucleus, the plus charge pulls the electrons in. The plus charge pulls electrons close. And you don't have to know that for the final, you just need to know what the trend is. What group of elements are the peaks for electronegativity? And we'll give you, actually we're going to give you the chart on the test, and it turns out that these are going to be the halogens. That's going to be fluorine, that's going to be chlorine, and I think bromine is the next. Oh, there's my hidden periodic table. And bromine would be the next one. The noble gases have 0 electronegativity. They have all the electrons they need. They don't even try to get them. Number 12, what group of elements are, I already did that one, okay. Number 13, what group of elements are not included on a graph of electronegativity values? That's going to be noble gases. Why not? They don't need electrons. Don't need electrons. They don't need more electrons. Don't need any more electrons. Scoot off the page. What are the trends for atomic size as you go across the periodic table? This is the one, the first one doesn't make sense. They get smaller as you go towards the right side of the table. That's because that positive charge is pulling them closer. As you go down the table, it does make sense. The atoms are getting bigger as you go down. So that's the trend. I guess you would say it's just the opposite electronegativity. The bottom left corner are the biggest, and the upper right corner are going to be the smallest. So, and you may get a question like this on the, in fact, I think there are in the final. Which element, period 2, is going to be bigger, calcium or strontium? And I think that was one of our starter questions. Strontium's lower, it'll be bigger. Which element's going to be bigger, strontium or yttrium? Did I say smaller or larger? Yttrium's going to be smaller, strontium's going to be larger, because as you go to the right, the elements get smaller. So that's the trend there. And I think I'm about to end part 1 because it's going long here. Yeah, we're at 14. Wow. All right, let's see. Name the particle emitted in alpha. Okay, that's going to be a helium nucleus. Beta, it's an electron. Or gamma radiation, that's just energy. It's a ray, not a particle. And we tend to draw those as helium with a mass of 2 and 2 protons. And the beta one, we can put a 0 charge and, 0 mass and -1. You zoom in there so it's easier to see. What's the charge? What's the change in atomic mass when an atom emits an alpha particle? An alpha particle has a mass of 4, so atomic mass decreases by 4. It gets smaller by 4. That's for an alpha particle. When a beta particle is emitted, the mass number does not change. No change with a beta particle, because that's where you're getting a neutron is changing into an electron and a proton. Oops. And protons and neutrons have the same mass, so you don't lose any mass there. Draw and order the penetrating abilities. Well, let's see. Paper, cardboard, and lead or cement. Cement, lead. And let's see. Alpha particles are stopped by this. Beta particles can go through to here. And then gamma rays can go into, and even sometimes even a few of them come out. What's the charge on an alpha particle? Well, it's got 2 protons, so an alpha particle has a +2 charge. A beta particle is an electron. It has a -1 charge. And a gamma ray has no charge, so it's neutral, 0. What material is necessary to stop an alpha? Okay, we just drew the diagram. Paper, beta particle, okay. Now, cardboard. And actually what I found when I think I needed a stack of about 100 test papers, still we're letting beta particles come through. Gamma ray, you need a lot of lead or concrete. Okay, finish these up and then I'm done. What particles needed to complete this reaction? Well, let's see. You've got a total atomic number down here when you add these two up of 5. So 2 plus 3 is what we need to put there. And that's going to be the element lithium when you look on the periodic table. We've got a total of a mass of 11 up here. So 11 minus 4 I think is 7. So that would be lithium 7 would be what we need there to complete that one. And the way you just make sure those two numbers need to equal those two numbers, just as these two numbers down here need to equal those. Got mercury plus hydrogen or break. Okay, so it looks like we're getting an alpha decay here. So we've got to make sure that we got 81 over here, and I think that's going to have to be 79. We've got 202 over here, so I think that's going to be 198. Correct me if I'm wrong, period 2. I think I got, is that, and that's gold. I think we went over this in most classes, so you should be good with that one. All right, almost done. We've got the mass number, the atomic number is increasing by 1. So that's telling us this is a beta decay. The mass isn't changing, so we just need to write in the beta particle, which is an electron, and I'll do it here with the beta symbol instead of E. These two numbers add up to 82. Those two numbers add up to 209. All right, the last one. In this reaction, what does the letter C? That's the mass number. What does D represent? That's the atomic number, which is protons, and mass number is protons plus neutrons. All right, I'm going to stop it there. Thank you. Goodbye.